Okay, the whole point of this hopefully pretty brief lecture is just to give you a review of directed graphs, actually, pretty much. I'm going to assume that you know what graphs are already. There you go, directed graphs. So here's an example of a directed graph, and I'm sure you are very familiar with the fact that it has a bunch of nodes, right? So let's see, what do we got here? We got Q3 is a node, Q5 is a node, Q6 is a node, Q1 is a node. I need to put on my other glasses. There we go, that's better. And we talk about also arcs that are outgoing arcs from nodes and are also incoming arcs to other nodes. So this arc here is an outgoing arc from Q0, incoming arc to Q1. We will sometimes use some special symbols to indicate, say, a start state or a start node. This little input triangle is one way I do it. I also will sometimes use just like an input arrow like that. I don't mind. We can agree that we'll all understand if we do it either way, as long as we keep it clear. There is, however, this concept of a neighbor, and you need to be careful with a neighbor because the idea with a neighbor is that if you have your arc is a pair, right, from N1 to N2, N2 is a neighbor of N1 if there is an arc from N1 to N2, but that doesn't mean it goes the other way. So for example, let's look here. Q5 is a neighbor of Q6 because there is a path, an arc from Q6 down to Q5, but Q6 is not a neighbor of Q5 because there's no direct arc from starting at Q5 and going to Q6. So our neighbor arcs go in one direction. Now here, of course, Q0 and Q1 are neighbors in both directions, right? Because there is an arc from one place to the other. And often we'll see these weights on the arc that tell us something about the problem that we're doing, the cost of that, of taking that arc. And again, I may sometimes say, say I have a vertex or I have a bunch of vertices instead of nodes. That's fine. You can use either language. I may say I have a bunch of edges instead of arcs. That's also fine. You know, I think the textbook uses nodes and arcs, so that's why I use this language, but we all will understand each other if we say vertices and edges instead. That's fine. And just some more terms that you just need to be very familiar with, right? It's old stuff. You just need to remember what we call it. So we talk about a path if we have a sequence of nodes for which every node in the sequence, right? There is no node there. I should probably erase that. That's not an eraser. That's a pen. There we go. So for which each node in the sequence, there's a pair between them. So we have here, for example, N0 has an arc to N1, N1 has an arc to N2, blah, 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 all the way up to NK. So specific path in our drawing, we could say that there is a path. Ooh, I'm in white. That'll work, I guess. Let's see, what do we got a path from? We got a path that starts at Q1 and then goes to Q6. And from there, we'll go to Q3. And then maybe because I'm feeling goofy, I will go back to Q6. And that is a path. It's a path from Q1 to Q6. It's kind of a circuitous path because we went via Q3, you know, and we visited Q6 twice, but it still counts as a path between Q1 and Q6. And the length of this, take a look at what we've got in here. So if we start at N0 and we go to NK, the length is K. The length is just the number of jumps you take, right? So the length of this path is actually 3, not 4, right? Because here we started 0, 1, 2, up to K, and here we did 0, 1, 2, 3. Now, you're always only going to have one start node. It may be indicated by this triangle. We may have that arrow, but there's always exactly one start node, only one start node, one start state where you're starting your problem. However, you may have multiple goals, right? I've got multiple goals in here. And the goals are just states that satisfy your problem. So whatever it is you're trying to do, if you get to the goal state, life is golden, you are good, right? And so given a start node and a set of goal nodes, we can talk about a solution, right? A solution to our problem, and our solution is just going to be a path from the start node to the goal node. So for example, my start node is Q0. If I want to get to Q5, one of the solutions that I might use would be starting at Q0, go to Q1, go to Q6, go down to Q5. That's totally fine. But there's nothing wrong with saying that the solution of getting to Q5 is going via some bizarre path, right? So we could go Q0, Q1, Q0, Q1, Q0, Q1, Q5, right? And, oh, I can't go down to Q5 like that. How did you let me do that? I hope you were yelling at me as I was doing it. So Q0 to Q1 to Q0 to Q1 to Q0 to Q1 to Q6 to Q3. I guess we have to go back up to Q6 and then down to Q5, right? That's a perfectly reasonable solution, though on the way we passed Q1, and all we really need for our solution is a path from the start node to any old goal node, right? So the best solution, not necessarily best, depends on what our criteria are, but the shortest solution in this particular problem is start at Q0 and go to Q1, because Q0 is the start node, Q1 is a goal node, so the path Q0 to Q1, which also happens to just be a single edge, is indeed a solution to our problem, to this graph. So I really want you to be able to look at this kind of a mathematical equation. It's important, and understand what it says. In this case, it's pretty simple, right? I was calling these things like the 9 here and the 18 weights before, but another term for them is a cost, right? Your book will use the term cost. And so we say, okay, cost is a function that takes an edge as a parameter, right? And cost is also a function that takes a path, right? So a cost can take a single arc, or it can take a whole path. And if we have a path that starts at n0 and goes to n1 and keeps going until it gets to nk, the cost of that path is, right, what do we got? We got the sum of I equals 1 to k of each of these individual edges, right? Each of the individual arcs. Notice that we've got I1 here so that we could start at 0, right? And that is just the same as the cost of each of those individual arcs added up together, right? So you should look at this and you should say, all right, I totally understand what the cost is, right? So for example, if I'm trying to go from Q0 to Q1, the cost there is going to be 9, right? We'll indicate the cost by little numbers on the arcs often. Though we could also have another path from Q0 to Q1, right? Which is start at Q0, go to Q1, go to Q0, go to Q1, go to Q0, go to Q1. And the cost of that path is going to be, how many times did I did it, you guys? I hope heard it, but, or you can figure it out for me, right? But we have the 9 plus the 18 plus the 9 plus the 18 plus the 9. I think that's how many times I did it. And you just add all those numbers up and you get your answer. Or if I wanted a path from Q5 to Q6, right? Well, it looks like there's actually 2 different paths that I could take that don't have any loops, right? One of them is I go from Q5 to Q1 to Q6. That costs me 1 plus 5, which is 6 units, whatever that is. Or it looks like I can also go from Q5 to Q3 and up to Q6. And that's only 4, so that's cheaper by whatever my metric is, right? So I'm not sure, I may have said a loop instead of a cycle, but again, there's another word that I'm going to use 2 different words to mean more or less the same thing. Well, to mean identical things, right? It's just a non-empty path where the last node in your path is the same as the first node in your path, right? And that's exactly what this says here, right? So just make sure you look at this and you say, oh yeah, I get it. That's a path, and n0 equals nk. We're going to talk about forward branching factor of a node. You may have heard that called the out degree of a node, right? The forward branching factor of a node is just how many outgoing arcs are there from that node. So for example, if we pick one of these nodes here, let's see, so Q1, which is this guy, if we say what's its forward branching factor, how many outgoing nodes are there from Q1? Well, there's this one. That's 1. And there's this one. That's 2. And there's this one. So the forward branching factor of Q1 looks like it is 3. And the backward branching factor is just how many incoming arcs are there. And so if we look at that for Q1, it looks like we've got 1 here and 1 here. So the in degree of the node, or the backward branching factor of that node, is 2, right? And we are going to make an assumption that will turn out to be important at some point, that our branching factors are bounded, right? So that means there is always some positive integer that is greater than or equal to all of the branching factors of all of our nodes. Excuse me, and that just lets us make certain assumptions that are tremendously useful.